Tamam, yani buraya bağlarsan önden bir konuşma yapalım. Bir 10 dakikası var çünkü. En azından bilgi verelim. Şu anda canlı yayına gerek yok. 10 dakikamız var. Konuşacağız. Benim teknikteki arkadaşlar, Lütfi hocamız sistemde mi şu anda? Beni duyuyor mu acaba? Tamam. Tamam, 10 geç o zaman başlayacak şekilde bekleyelim. Tam zamanında başlarız. Tamam.
Saat dakikasında gel. Dakikasında. Ben seni 25 dakika bekliyorum da 2,5 saatte gelmiyorum.
Merhaba Lütfü Hocam, sesimi duyuyor musunuz?
Evet, ben sesinizi duyuyorum. Merhabalar.
Merhabalar, hoş geldiniz.
Hoş bulduk.
Şimdi bunu ben yönetiyorum, adım Hakan Gül. Sizden önceki sunu gelemediği için sunu sahibi, şimdi 10 geçe başlayacağız tam zamanında. Bir ara verdik. Şimdi
Tamamdır.
konuklarımız geliyor, 2-3 dakika içinde başlayacağız. Tam 10 geçe başlatacağız.
Peki,
Bir
çok
dakika.
teşekkür ederim.
Tamam.
Nasıl Ankara'da havalar nasıl?
Gayet iyi. Çok güzel bir sonbaharımız var. Biraz serince ama güneşli.
Çok güzel, çok güzel. Sevindim. Orada olmak isterdim.
Evet, siz neredesiniz şimdi hocam?
İstanbul'dayım.
Tamam, tamam. Teknikteki arkadaşa başlayabilir miyiz? Hazır mı sistem?
Şimdi ekranı paylaşacağım ama yüklemem lazım herhalde slaytı.
Siz o hazırlığınızı yapın.
Evet, tamamdır.
Tamam hocam, gayet iyi. Ben sizin isminizi şimdi size sunacağım. Ondan sonra başlarsınız. Yaklaşık 30 dakika süremiz var. Ona göre görsek alıyoruz.
Peki, teşekkür ediyorum.
Okay, let's start. If the last presentation of the morning session is going to be given by Dr. Lütfi Arda. Dr. Arda, Professor Arda.
Okay, thank you so much. Today I will present my presentation. Title is the role of defects on structural and optical properties of zinc oxide nanorods synthesized by hydrothermal route at various growth times and the temperature. This work were done by Şeyda Kaya, Özgür Öztürk, Ahmet Taşçı. They are from Kastamonu University. Fatih Bulut, he is from Sinop University. Doğan Akcan and me, Lütfü Arda, we are from Bahçeşehir University. That means this work was collaborated with 3 universities. First, I will give you what is the motivation about this work. This work is about the zinc oxide. It's, briefly, I will define this motivation. Among the metal oxide, semiconductors such as tin oxide, indium oxide, vanadium oxide, titanium oxide, zinc oxide having approximately 37 electron-volt band gap and 60 milli-electron-volt exciton binding energy has received considerable attention as a promising material in various applications, including optoelectronic devices, spintronic devices, nano-electromechanical system, nano-generators, and nano-sensors. Zinc oxide is also a visual transparent conductive oxide. And it is using if you look from the cheap part, it is better than the indium oxide, and it is widely used in the touch screen, flat panel, display, thin film, transistor, organic light emitting diodes, surface acoustic wave devices, and the solar cells. In addition to the superior physical properties of zinc oxide, it is also an environmentally friendly, biocompatible, non-toxic material, and it is natural abundance, low cost, and easy synthesis methods make the material suitable for large-scale production. For the fabrication of zinc oxide material, knowing the properties of vacancies and defect is crucial for device production since they provide a variety of division mechanisms. It is well known that optimize the electrical binding and optical property of zinc oxide, which strongly depend on the impurity and defects in zinc oxide materials. Defects that occur in materials depends on the preparation methods, the doped element, the temperature, and the growth time. In order to use zinc oxide more efficiently in the industry, it is necessary to optimize the chemical characteristics of zinc oxide. For example, its crystal structure, homogeneous size, distribution, and different shapes like the nanoparticles, as a plates, as a flower, wires, rod, as a flakes, as a thin films. That is a this example give us the dimension, is a 0 dimension, 1 dimension, and 3 dimension of materials. In this is a work we use 1-dimensional zinc oxide material due to the surface to volume ratio and the sensitivity of surfaces increased. Okay, and there are various methods to fabricate 1-dimensional zinc oxide nanostructure. Such as a vapor, liquid, solids, is a growth, metal, organic, chemical, vapor deposition, pulsed laser deposition, solution-based synthesizers is one of the most reasonable methods. Because of its simplicity, simple equipment, and low temperature requirement. Among the solution-based synthesis, the hydrothermal route is widely used to fabricate zinc oxide nanorod with a variety of morphology, such as a flower-like, pencil-like, and pyramid-like. In this method, there are many synthesis parameters, including seed, deposition, growth temperature, growth time, is a molarity, etc., which are important in governing the structural properties of the films. The structural property of zinc oxide thin films strongly depend on the crystal quality of this compound and impact the optoelectronic characteristic in surface engineering application. Moreover, in the hydrothermal route, it is expected to manipulate the optical oxide nanorods by changing only the synthesis parameters without letting go or adding any impurity to the crystal structure. In this work, we will use is a hydrothermal route. Okay, and it's a very important question in this work is the fact that occur during growth in this nano-sized material are still in incomplete issue, and we search defects on the fabricated materials. Which is the aims of the present work? Let's explain this. We focus on the relationship between the synthesis parameters, is the temperature and the growth time and the role of defects on structural optical properties. We synthesize the zinc oxide nanorod using a hydrothermal route at various temperature and growth times. The defect density of zinc oxide nanorod manufactured by the hydrothermal route is investigated by the Gaussian decomposition of the PL spectrum. PL means is a photoluminescence spectrum. We also investigated the changes systematically in the optical properties concerning the structural and defect evolution of this compound. We observed that optical properties, including visible transmitters, the band gap is easily organized by changing hydrothermal growth time and the temperature. material and the methods. I told you that we use hydrothermal route. That means zinc oxide nanorod were fabricated by using this method. All chemical used in the experiment were taken from the Sigma Aldrich. Glass substrate were used for the growth of zinc oxide nanorod arrays. The fabrication process is shown in the figure. Two different zinc oxide nanorods were fabricated. One of them is a just nanorods. The second one, we fabricated nanorod on the seed layers, and seed layers was on the glass substrate. It's a lot like the nanorods on the fields. Okay. How we can fabricate it? It's a nanorod on the zinc oxide seed layer. Okay. First, we clean. It's a glass substrate using ethanol and deionized water. Then the social method we use to prepare the solution for the seed layer. The seed layer was as a zinc oxide. That means we use as a precursor material zinc acetate, and it's a methanol was used as a solvent, and monoethylamine was used as a salt stabilizer. Then all this material placed on the beaker, and we stirred all this to when we get is a transparent solution. We look at the figure. We dip it inside transparent solution. Okay, then we try this dipping and the withdrawing process 5 times, and we coated it's a zinc oxide thin film on the glass substrate. But there is the solvent evaporation. We did it using furnace, and the furnace temperature is 600 degrees Celsius for 30 minutes. After annealing process, look at this part. Can you see my cursor here? This is that substrate. On the substrate there is the zinc oxide thin film. Okay. For the nanorod, I'm sorry. Yeah, I did it. Okay. How we synthesize nanorods? Okay, we use 0.1 molarity of zinc acetate dehydrate, and 0.1 molar of hexamethylene tetramine. All this precursor were dissolved in distilled water and stirred to form a transparent solution at room temperature. Look at the beaker, these two precursors, and we stirred 1 hour mixing this. Okay, the mixture was transferred to a Teflon lined stainless steel. Look at here. Oh my God, very good. Here, stainless steel autoclave, and the substrate were vertically dipped into the solution. Zinc oxide nanorods were produced at different reaction times as 3 hour, 4 hour, 5 hour at 90 degrees Celsius, and different reaction temperature as 90 degrees Celsius, 120 degrees Celsius, 150 degrees Celsius for 3 hours. Finally, deionized water was used to wash the substrate, which were dried in a vacuum furnace at 60 degrees Celsius overnight. As a result, we get as a nanorod on the zinc oxide thin films. How about the just zinc oxide nanorod? We didn't use the glass and the zinc oxide sheet layer, just it's the second part. We put it's a zinc acetate dihydrate and hexamethyl tetramine. It's in the Teflon lined stainless steel, and then we heat treated this. We get only zinc oxide nanorod. Then we fabricated this nanorod. We have to characterize them and look at this experimental procedure. We use 3 different characterization part. One of them characterize the zinc oxide nanorod using XRD, scanning electron microscope, and the EGS. Second, we found its optical properties of this materials, and then we use photoluminescence measurement to find its impurity and other dislocation and defects of the material, how they changing with the temperature, how they changing with method, how they changing with the growth time, and I will give you how they change it in this work. Okay. After this part, when we fabricated its zinc oxide nanorod, first key question is whether the resulting material is indeed a single phase of zinc oxide. That's why we took X-ray diffraction for the zinc oxide nanorods. Look at it's a figure 2. There are 2 figures, A and B. Diffraction pattern of zinc oxide nanorod produced at a different growth temperature, A part in the left side, and the B part different growth times there. And the inset show the total variation of C lattice parameter, growth parameter, time, and the temperature. I want to discuss this part. It's shown in these figures. The XR spectrum of zinc oxide nanorod, it's a nanorod, it's a peaks. You can see only 3 peaks. They are 100 peak and the 002 peak and the 004 peak, and their position corresponds to a typical zinc oxide bruchite crystal structure. There is no secondary peak. That means that there is the only zinc oxide structure, and the sharp peak is the 002 peak. Was detected for all zinc oxide nanorods, confirming the preferential orientation of the grains along the C-axis, which is orthogonal to the substrate. Also, when we look this, it's figures, the intensity of 002 peaks increase with an increase in growth time. Okay, growth time is the A figure in the left side, and the second figure is the growth temperature is the left side, and the growth time is the B part. This can be credited to a better crystallinity of the film. Moreover, the crystallographic parameters found from the diffraction pattern were found, and they are given in the table. In the next slide, I will show you this table, besides using the scanning electron microscope images. Also, we checked its nanorods, its diameter and the lengths, how they changing with the growth time and the temperature, and also I will show you in the next slides. Let's show this. Look at here. This is the critical parameters and grain size of zinc oxide nanorods obtained from the diffraction pattern. Look at is the first column is the sample. It's a nanorod. Is a growth time is 3 hours, 4 hours, 5 hours, and the temperature. Growth temperature is 90 degrees Celsius, 120 degrees Celsius, is 150 degrees Celsius. And the second column is the 002 peaks is a center. And the third column is the formula with half maximum. We calculated grain size, also C lattice parameter, and the stress is for the each nanorods. And this table is diameter, length, and aspect ratio for the zinc oxide nanorods for the 3 growth time and the 3 different temperature, diameter and the length and the aspect ratio. Okay, let's turn again to the table 1. From the table 1, look at the C lattice parameter. Decreased it's from 5.195 to the 5.192 Armstrong as growth time increased from 3 hours to the 5 hour. Conform a slight reduction in C values with increasing growth time. And this is a C parameter I drove in the above. Let me check here in the inset. Look at the C parameter growth time, and the C parameter is a growth temperature. You can see all this. This reduction in the C lattice parameters can be associated with compressive stress, and also calculated compressive stress of the samples, which occurs owing to increased temperature and the growth time. Moreover, 002 peaks of the samples shifted toward the higher 2 theta angles as the temperature and the growth time increase in crystal structure. The compressive stress occurring in the direction parallel to the surface may affect the lattice properties in the direction perpendicular to the surface, which appears with the shifting of diffraction peaks. Also, the last column is we calculated stress is values, and look at the sign. All of them are negative. That is negative sign indicate that the stress on the C axis is compressive. The compressive stress increased from 0.871 to the minus 1.132 gigapascal as the growth time increased. Look at the growth time, 3 hours to the 5 hour. Although the change was observed in the stress value of zinc oxide nanorod for the temperature 90 degrees and 120 degrees, when the growth temperature reached 150 degrees, it was found minus 2.70. I thought in the material part, we use a sheet layer, and this zinc oxide sheet layer coated on the substrate before the hydrothermal growth to prevent the lattice mismatch between the substrate and the nanorod which create various structural defects on the film surface. Despite this, unhindered thermal and elastic mismatch strength could be responsible for the residual compressive stress in the crystal structure of zinc oxide. Also in the table 1, there is a formula with half maximum. And the shrinkage of the width of the peaks is the growth time, and the temperature increase indicating a particle size increase. After this is a XRD result, we measured scanning electron microscope, and we checked surface and the cross-sectional of the nanorods. Look at here. In this is a figure. Is the left side. This is the surface. Is a scanning electron microscope of the top view, and the right side there is the cross-sectional scanning electron microscope, and you can see easily all nanorods on the zinc oxide thin films. Look at also this is a scanning electron microscope ABC. This is a scanning electron microscope. The figures are for the growth time, and the DEF is figures are for the growth temperature. All these same images reveal that the zinc oxide nanorods are grown perpendicular to the substrate. A perfect hexagonal structure is observed for the nanorods growth at different times. It's as can be seen in the figures. Okay. Also, note that the hexagonal structures start to deteriorate. It's resulting in secondary inflation on the top of the rod as growth temperature increases from 90 degrees to the 120 degrees. When the temperature reaches 150 degrees, pyramids, look at the last, it's a figure, pyramid-like structure are found, okay? As it is well known, zinc oxide consists of polar and non-polar crystal plane, which affect the growth habit of its one-dimensional nanostructures, such as the nanorods. Also, we can conclude that temperature has a strong effect on the axial and literal growth rate of crystal plane. The difference in the growth velocity between these polar and nanopolar planes could be responsible for pyramid-like structure. After it's the same images, okay, I will back to the table to this diameter length and the aspect ratio for zinc oxide nanorods. From this table, you can see that same images given in the previous scanning electron microscope figures. We calculated the diameters and length of nanorods. I will give you numbers. Okay, look at the diameter of the growth temperature. That means when increase growth temperature, diameter of the nanorod increases. Also, when increases growth temperature, 59 to the 88, diameter also increases. Length also increases only in the 150 degrees Celsius temperature. Length decreases, and the aspect ratio, when we look the aspect ratio decreases with the growth time, and also increases with the growth temperature. Okay, how many times I have?
5 minutes.
Okay, Because I have a many slides. Okay, let's go fast. Okay, this is the EDX. I'm sorry for this. This is the EDX mapping images of zinc oxide nanorods. Okay. The elemental distribution of the elements and the second slide. The first one is a mapping, the second one EDS mapping spectra and different distribution rate of zinc oxide nanorods, growth at 90 degrees Celsius for 3 hours. Let's move to above, okay. The purple, yellow, and green phases correspond to the zinc as oxygen and the silicium, respectively. According to the mapping result, the sample contains only 2 elements, zinc and the oxygen, confirming that no elemental impurity is observed. Silicon peak appearing in the spectrum comes from the glass substrate. Also, it can be said that the elemental distribution is quite homogeneous in zinc oxide nanorod arrays according to the data given in the next slide. In this figure, the elemental concentration of zinc and the oxygen are 77.33 and the 18.67 at weight is a percent respectively, while they are 46.83 and the 47.46 at atomic percent. We characterized all nanorods, and the next step is the optical properties. Okay, and the optical properties, the optical transmittance spectra of zinc oxide nanorods are given in this is 2 figures. Okay. As can be seen from the figures, all the sample exhibit high transmittance and the visible region and the low transmittance in the ultraviolet region, which is a typical properties of zinc oxide. The values of average optical transmission, I will give you next slide. Okay, this is the transmittance and the band gap of the samples. According to the table, for the sample grown for 3 hours, the average optical transmittance corresponds to about 86%, indicating that the film is transparent in the visible region. Visible region means it's between 400 and the 800 nanometer. This relatively high optical transmittance in the visible region decreases as growth time increases to 5 hours. The decrease in transmittance with the increase in growth time was observed quite frequently in the previous studies. According to the figure in these 2 figures here, for sample growth at 90 degrees, the average optical transmittance in the visible region is about to 86%. Which decreased to about 62% as the growth temperature increased to the 150 degrees. After that, what is the change in transmittance of the nanorods? We can explain like this. Many parameters affect the optical transmitter characteristics of one-dimensional zinc oxide nanostructure. The most crucial ones can be given as a surface roughness, field thickness, crystal defects, oxygen vacancy, and impurities. In our study, okay, optical transmittance value depend on nanorods diameter and the length. I show you in the table 2 Also, it's a band gap and the transmission I showed you in the previous table, table 3. The average optical transmittance and the band gap value decreases as the diameters and lengths of nanorods increase consequently. The volume of nanorods increases, thus, the decrease in transmission may be related to the higher zinc oxide nanorods volume and the higher number of defects and the increase in film thickness, which is consistent with early literature reports. Besides, it has been shown both theoretically and experimentally that the surface roughness has significant effect on the optical transmittance of the thin films. Thus, it can be said that the multiple random optical scattering on rough surface may be result in lower transmittance in zinc oxide nanorods. The increment in both thickness and roughness of zinc oxide nanorod with increasing temperature and the growth time was reported in our previously study. After that is after transmittance, we calculated band gap of the nanorods using half plot method, and it's, this band gap I showed you in the where is this? Yes, band gap. Look at the band gap. Band gap of the nanorods. It's increased with the growing time and decreasing with the growing temperature. After this, okay, this is about the optical properties and the last measurement. What is the time? Can I continue 5 minutes more? Is it possible? This is the okay. That is after that. Okay, optical properties. It's a photoresistance properties. We measure. It's my sample photoresistance. It's properties. Why we use it's a photoresistance study. To study the crystal quality, defect type, and the defect density of a semiconductors materials, the photoresistance spectra are widely used. Also, it's an electron spin resonance is used for the defects. It's in this work we use only photoresistance spectra, but we have also some study about electron spin resonance. Okay, therefore, photoresistance measurements are performed to analyze the effect of growth time and the temperature on the photoresistance properties of zinc oxide nanorods. Hexagon arc lamp is used to the light source, and zinc oxide nanorods are excited at 365 nanometer. Okay, and it's right now in my slide, you can see photoresistance spectrum of zinc oxide nanorod produce at different growth times in the left side, and the B figure is a different growth temperature. And when we look at this is a figure, there are two dominant emissions, sharp ultraviolet emission peak on the left side, and both visible emission band on the right side. This band corresponds to the typical N-type zinc oxide semiconductor. Ultraviolet emission is responsible for the crystallization quality and the defect quantity of zinc oxide, and visible region emission. This is the deep level emission also is in charge of originating from defects. Beside a few peaks were observed between 450, look at here, look at these a few peaks. There are few peaks be between 450 nanometer and 500 nanometer, which came from the use of the hexagon lamp. In the UV region, a sharp transition peak corresponds to band H emission was observed at around 392 here, 392, this peaks to the 395 nanometer for zinc oxide nanorod. This emission in the UV region generally was attributed to the near band H transition is as a common optical property of a wide band gap of zinc oxide. Also, we can measure band gap using the PL measurement result, but correct one is using with the tau plot. Okay. Near band emission originated from the excitonic transition between electrons and the holes in the conduction band and the valence band, respectively. The stronger ultraviolet emission is observed in the zinc oxide with the higher crystallization quality and lesser defect. This is important for the crystallization quality of the samples. At the growth time of the 4 hour is a green one, okay? Zinc oxide nanorods exhibits the lowest near band emission. Look at the left side. While a significant increase in this emission was observed with the growth time of 3 and 5 hours, the highest UV emission was observed at the growth temperature of 150 degrees Celsius, while the lowest one was observed at 120 degrees Celsius. Thus, the growth time and the temperature increment improved the crystallization quality of the zinc oxide nanorods. Okay. The second
time is, could you please? Yeah.
Just give me 2 or 3 minutes, okay? I know. Give me 2 or 3 minutes, okay? I will conclude all this. The second dominant broad emission band, because this part is a very important, and this is the center of my work, okay? The second dominant broad emission band is a visible region. The deep level emission is assigned to impurity of defects, including oxygen vacancies, zinc interstitial, zinc vacancies, oxygen antisite, and the oxygen interstitial in zinc oxide crystal structure. These defects are divided into 2 parts. Zinc interstitial and oxygen vacancy are donor, and zinc vacancy, oxygen interstitial, and the oxygen antisites are acceptors. A decrease in DL peak intensity was observed as the growth time and the temperature increased. This result can be attributed to the reduced defects in the zinc oxide crystal structure, which is also supported by the XRD analysis. However, as seen in figure 7, left side A and the right side B, it is very difficult to get information about how the defects change in the visible region. Okay, that means in the deep level emission, we cannot understand how defect changes. Therefore, a detailed examination of the origin of the defects in the visible region is required in the literature. The visible emission of zinc oxide originated from defects were extensively studied by the researchers. The underlying mechanisms were still not fully identified. Therefore, the photoluminescence spectra were subject to Gaussian decomposition to the subpeaks according to their origination. And okay, we use a physics program. And again, we drove Gaussian decomposition of photoluminescence spectra of the zinc oxide nanorods at different growth time and the different growth temperature. This and from these 2 graphs, okay, Okay, I will pass, or it's okay, I will not explain separately this. We conclude that, okay, this result. Let me check again this fix. Okay.
Gelsene benim odaya bir.
The growth temperature plays a crucial role in reducing oxygen defect in zinc oxide nanorod. This outcome is also in excellent agreement with the XRD spectrum. Generally, crystal structure defects are detected repeatedly in the one-dimensional zinc oxide nanostructure produced by hydrothermal synthesis using low growth temperature. Accordingly, we can conclude that the responses in the hydrothermal method may pose the double charged oxygen vacancies and oxygen interstitial, and thus affect the luminescence property of zinc oxide nanorods. Source: zinc oxide nanorods should be fabricated by choosing the appropriate time and the temperature according to the fact, donor and the acceptor, depending on the usage place. That is okay, and I will show the conclusion here. Just I will say that the simple and inexpensive hydrothermal route could be used to obtain zinc oxide. Let's use this nanorods with good crystal quality. And the last slide is, okay, many thanks to Bahçeşehir University, Sinop University, and Kastamonu University. Thank you for your attention. Really, I was really sorry because my time was exceeded. Thank you so much.
And thank you very much for your impressive and informative talk. Since the time is over, indeed, unfortunately, there is no time for the questions, but if anybody has a question, he or she can directly reach you from your university, I think. Again, thank you very much.
Please send to me email if you have any questions. I will be appreciated, all of you.
Thank you so much for your contribution to the Congress. Bye-bye.
Okay, thank you so much. Take care and see you one day in the Gazi University, I think.
Okay.
Take care.
Bye-bye. Teşekkürler katıldığınız için. Kolay gelsin.
Sağ olun.